So in this video we're going to continue the discussion we were having on continuous functions and the different classes of continuous functions. Let's talk about some others. Let's talk about a linear combination of functions. We know what a linear combination is. It doesn't matter if you guys don't, but let me just explain it to you. A linear combination is basically one constant a1 being multiplied by another function f1. We don't know what this function is. We don't care at this point, right? We're going to add this to another constant a2 times another function f2. So think of it as, I don't know, 4x plus 7x, right? But that's not entirely it. It could be 4x plus e to the power x, or 3x plus cosine of x, right? It could be a linear combination of functions, but that's not it. It could be extended to multiple functions, not just two. So let's extend this argument to n functions and n constants consequently, right? So basically this is a linear combination of functions. So what I'm saying is that if we have f1, f2 all the way up to fn functions that are continuous at a point x equals p, then their linear combination that we've expressed above, right, is going to be continuous as well at x equals p, using the rules that we talked about in the previous class, right? This is something you guys should know by now, because we've seen that no matter what operation we apply, except the quotient, which we're going to talk about now, nothing about the function changes. It still remains continuous, right? Operators such as addition, subtraction, multiplication, things like that, right? So another example. Now that we're going to talk about polynomials. Polynomials are mostly continuous. Actually, all polynomials are continuous. So we need to define what a polynomial is. Let's talk about this linear combination thing. But before that, tell me, is x a polynomial? We know that x squared plus x is a polynomial, right? What about x cubed plus x to the power 4? What about 1? As it turns out, all of these are considered to be in the class of polynomials. So there's a general formula for polynomials. It's a constant a, right? It could be, it's a0, it's the 0th constant, right? It's multiplied by x to the power 0, right? We have a constant a1 multiplied to x to the power 1, a constant a2 multiplied to the power x2, right? This goes on and on up till we reach an times x to the power n. So if you think about this formula, you can express any polynomial in this form. If we have n equals 2, think about it. If you have n equals 2, what happens? We get the equation a0x0 plus a1x1 plus a2x2, right? That's basically saying a is a constant times x squared plus a constant times x plus x to the 0 is 1, so a0. That is a quadratic equation, right? The only difference is we haven't assigned constants, so let's do that. Let's assign constants. a2 3 हो गया इस केस में, a1 को 1 रहने देते हैं, and a0 turns out to be 7. Still a polynomial. We just expressed it in a general form. So this could be extended to x to n terms, and consequently that would be a polynomial as well. What you guys need to know is that all of these, all polynomials are continuous. A very important fact. And we're talking about the different graphs we were getting in the previous video when we were changing polynomials from x to the power 0 to x to the power 3. So that similar argument would apply for polynomials, because as we're increasing the power, we're just getting different shapes. They're still continuous. The functions are continuous, but we're getting different shapes, okay? So now let's talk about the quotient rule. So the quotient of two functions is continuous. We know that. But there is a condition. The first condition is that f is continuous and so is g. They're both continuous. And at the same time, g of x cannot equal 0. Because if g of x would equal 0, then that basically means the function is not defined at that particular point, right? So it would be problematic in that case. But besides that, these functions turn out to be continuous. A class that is a subset of this quotient rule would be polynomials. being divided by polynomials. They are specially referred to as rational functions, right? And you guys might have seen them in this form, maybe x over x squared plus 1, or x cubed divided by x squared. That turns out to be x, but you see what the point is, right? So we have something else like x to the power 4 plus x to the power 3 divided by x plus 1. That's rational too. Two polynomials divided by each other. The condition is that rational functions are continuous only when the denominators are not equal to 0. So for this to be continuous, x squared plus 1 equals to 0 should not have a solution. मतलब if you solve this equation, you should not get a solution. और अगर x squared equals to 0 solve करें तो कोई solution नहीं आना चाहिए. But in case में x equals 0 आ रहा है, तो which means कि it's discontinuous at x equals 0. इस case में x plus 1 equals 0. If we solve it, we get x equals minus 1, which means it's discontinuous because when I plug in minus 1 over here, I get 0 in the denominator, which is problematic. So since we're talking about this, there's an important concept in calculus and in math basically, which talks about redefining the domain of a function. So what I'm basically saying over here is, if I have sine x over x, right, and we know that f of 0 does not exist, right? Not exist, but that causes the function to be discontinuous. So what if I was to take 0 out of the domain? So right now the domain is all real numbers going to real numbers, right? Matlab, you put in any real number here and you put in a real number here, you divide it out, you get a real number. But what if from the real number set I subtract or I take out the element 0? What happens then? As it turns out, in that case, it would be continuous. Because 0 would not be an element of the domain anymore. So there's no need to plug in a 0 over here. And as we know, there are parts of the graph, like all other parts of the graph, in sine x over x are continuous except x equals 0. But since that's out now, this version of sine x over x is continuous. Weird, right? But that's the important concept that you guys need to grasp at this point. The concept is that you redefined the domain in such a way that you made the graph continuous. You redefined it. It wasn't initially continuous, but you redefined it, and that caused the new function to be continuous. That's pretty much it for this video. In the next video, we're going to wrap up the rules and talk about the absolute value function and trigonometric functions that are continuous as well. So those functions are very important because they're going to be used in later discussions on the definition of a derivative, and it's vital that you guys go through the next video especially, because that's going to be used in the later videos for rules of differentiation that have to be applied and for proofs that you need to use in order to conclude that a derivative exists for a particular function, such as the absolute value function. So see you guys in the next video.